Hello everyone, I'm Cheong from BMI's lab in the Department of the Biomedical Science and Engineering. In this assignment, I'll present about set 3 from the 8 given sets, cross-validation and bootstrap. First, I'll briefly introduce the concepts of the cross-validation and bootstrap. Second, I'll solve a problem from the given material with a quick solution. And finally, I introduce my research area and then show you how Bootstrap and cross-validation are adopted in my research area. So let's get started. So before we start knowing about cross-validation, first we need to know about the validation set approach. This figure shows a schematic display of the validation set approach. Here, a set of n observations are randomly split into a training set and the validation set. The reason why we split the data set into training set and validation set is that the statistical learning method is fit on the training set and the performance is evaluated on the validation set. So here's the example of the validation set approach. On the left side, validation error estimates the single split into training and validation data sets. On the right side, the validation method was repeated 10 times. Each time is using a different random split of the observations into a training set and the validation set. The method on the right side seems related to low CV or K4 cross-validation, so I'll discuss it further later. So there are two cross-validation methods explained in the textbook. One is the live-on-out cross-validation, and the other is K4 cross-validation method. In this section, I'll explain the live-on-out cross-validation method. So the live-on-out cross-validation method estimate for the test mean square error is average of this n test error estimate. So as you can see here, the specific equation looks like this. And figure 5.3 shows a schematic display of live-on-out cross-validation. A set of n data points is repeatedly split into a training set, which is shown in blue, containing all but one observation, so excluding one observation. And the validation set that contains only that observation, which is shown in beige. The test error is estimated by averaging the n resulting MSEs, which is mean square errors. The first training set contains all but observation 1. The second training set contains all but observation 2, and so forth, 3, 4, 5, and ... n. So this is the live-on-out cross-validation example on auto data. So with least squares, linear or polynomial regression, an amazing shortcut makes the cost of low CP as same as that of the single model fit. So similar to single model fit. So additionally, this is the equation for this specific example. So in the later section, I'll explain about K4 cross-validation, and the equation might be similar. So I'll explain the difference between them later. So in this section, I'll explain another cross-validation method, K4 cross-validation. So this approach, so I'll read it through here. So this approach involves randomly dividing the set of observations into K-fold, CB, K-groups, or folds, or approximately equal size. The first fold is treated as a validation set, and the method is fit on the remaining K-1 folds. So the mean square error, MSE1, is then computed on the observations in the held out fold. This process is repeated K times each time. A different group of observations is treated as a validation set. This process results in K estimates of the tester, MSE1, MSE2, ... MSEK. The K for CB estimate is computed by averaging these values. So you guys might not understand by just reading this throughout. So I explain with the visualized examples in the next slide. Okay, so let's check the specific usage of this method. So the difference between low CB and K-fold cross validation is that N is the number of data points and K is the number of the sets of N observations. So K is larger than N with easier explanation. That is why the equation is similar between each other. So as you can see, K for cross validation, a set of N observations is randomly split into 5 non-overlapping groups. So 1, 2, 3, 4, 5. So let's see the bias-variance trade-off for K for cross validation. Since each training set is only K minus 1 divided by K as big as the original training set, the estimates of prediction error will typically be biased upward. So what is the reason why? So that is because this bias is minimized when K equals N rho CB. So K equals N multiplied by rho CB multiplied by N, but this estimate has high variance. So generally, K equals 5 or 10 provides a good compromise for this bias-variance trade-off. So, okay. So from now on, let's try to understand what the bootstrap method is. Suppose that we wish to invest a fixed sum of money in two financial assets that yield returns of X and Y, respectively, where X and Y are random quantities. So we invest a fraction of our money in X, and we invest the remaining 1 minus alpha in Y. So since there is a variability associated with the returns on these two assets, we wish to choose alpha to minimize the total risk or variance of our investment. In other words, we want to minimize bar alpha x plus 1 minus alpha y. So these are the equations of the bootstrap method for general, where sigma x squared equals bar x and sigma y squared is bar equals bar y, and sigma xy equals covariance x comma y. And in reality, head is located on the upper part of alpha and sigma. So that's the difference. So let's check how the bootstrap method is used. On the figure 5.10, on the left side, we can see the histogram of the estimates of alpha obtained by generating 1,000 simulated datasets from the true population. On the center, we can see the histogram of the estimate of alpha obtained from 1,000 bootstrap samples from a single dataset. And on the right side, we can see the box plots of them. In each panel, pink line indicates the true value of alpha. You can additionally find the result of the bootstrap by equation written on the right side. So alpha slash equals 0.5996, and the standard deviation made from this equation equals 0.083. So this is the last section of the concepts of cross-validation and the bootstrap. Here, figure 5.11 shows the illustration of the bootstrap approach on a small sample containing n equals 3 observations. So each bootstrap data set is So n equals 3, 1, 2, 3. So each bootstrap data set is used to obtain an estimate of alpha. And finally, the standard deviation of this approach comes out like this. So here comes like this. And the number of these components becomes same as here, B. Okay, so from now on, I make a proof for the bootstrap method. I prove this equation with my base knowledge of differential equation. So proof comes out like this. Okay, so now I'll explain it one by one. So first, let var alpha x plus 1 minus alpha y equal is let's assume this as var z alpha. Then var z alpha, which is same as is this equation var alpha x plus 1 minus alpha y can be re-described like this. So alpha square times sigma x square plus 1 minus alpha square times sigma y square plus 2 times alpha times 1 minus alpha times sigma xy. And rephrase it, and let's rephrase this equation to like this. So it looks more shorter. And then with this shortened equation, now let's use differentiation to find the optimized value. So we now use differentiation method. We focusing on alpha value. So let's differentiate it like this. And if you differentiate this equation, then it changes into this equation. So let's map this together with similar values, the same values. Then it becomes 2 times alpha times sigma x squared plus sigma y squared minus 2 sigma xy minus sigma y squared minus sigma xy. So to find the minimized value, we should assume var z alpha differentiated to 0. Then it should become minimized value. So and then 0 equals this equation, and so this part should be equal to this part. So it can be changed to here. So alpha sigma x squared plus sigma y squared minus 2 sigma xy equals sigma y squared minus sigma xy. And if you move this to this side, so this part should be divided by this part, then it becomes equation. It becomes the original equation like this. So it's same equation as here bootstrap concept. Okay, so let's move on to others. The next slide. Okay, this is a final section for my presentation. Real world application examples on my research area. My research area is EEG and EMG analysis, and also speech synthesis from these kind of biosignals. So I found 2 recent papers adopting the bootstrap and cross-validation. First, this paper, BERT, is published in 2024 and used the bootstrap method for calculating loss functions. So let's take a look. In this paper, they used the bootstrap method for each to language training for deconformer, which is the part of the full BERT model. Here, they adopted the loss functions for every specific test, word level, sentence level, and context level. Then where is the, so as you can see, this equation looks similar to here, bootstrap concept. Yeah, So make the fractions. Okay, so basic concept of bootstrapping can be make the adopt into making a loss functions like this. Okay, so then where is the example of the cross validation? I'll show you on the next slide. So this is a recent paper published in 2025, which used cross validation method. Graph neural networks for electroencephalogram, which is EEG analysis, Alzheimer's disease, and epilepsy use cases. So here they use cross validation method for binary and ternary classification of the seizure discrimination use cases. Let's take a look. So here's the explanation about the usage of cross validation method and the table summarizing the results. In binary, they got 99.84 test accuracy, and internally, they got 96.95 test accuracy. So here also same. So I realized that knowing the fundamental of this kind of statistical learning method like this are really important for contributing to these outstanding research. So in the future, I want to contribute for outstanding research with using these kind of fundamental statistical learning. So this is the end of my presentation. Thank you so much for listening to my speech, and always be happier. Thank you.